Hello community! I learned something new about AI, game theory, reinforcement learning, and I would love to share it with you. It is all about self-play. So we have multi-agent reinforcement learning, we have a Markov game, and we have self-play. And you remember, we had multi-agent reinforcement learning, and in my last videos, I focused on multi-agent imitation learning, and now we switch back to reinforcement learning. What is self-play? It is a real powerful technique here, and it enables agents to learn and master complex environments, particularly in games and scenarios where human-level strategies are real difficult to encode directly or require some exploration of vast strategy spaces. And we look at the later case, where we have huge strategy vector spaces, and our exploration of those spaces is the most important thing to learn strategies that are better than whatever we have currently. So in a self-play, an AI agent competes against version of itself, and it's continuously learning from this interaction. And this process allows the agent to discover and refine its own strategy over time, leading to a deeper understanding of the game mechanics of the problem space. And the beautiful thing is we do not need external data. We do not need, like in imitation learning here, the perfect expert that we can learn from, but we have now the possibility with computational resources to find here the optimal policy. And it is the perfect policy that we can here introduce new strategy or new counter strategy if we have multi-agent scenarios, which lead here to progressive improvements. So if we ask, why should we know about self-play? Training AI systems only on human-generated data, this can lead to an overfitting on the human strategy and on the human bias we have in the pre-training data. But if we have self-play, this allows an AI system to go beyond the human creativity and the human paths and explore completely new strategy that might be not intuitive or available to the human players, but therefore we have here the potential to discover complete new solution and complete new policies to our task. This is beautiful wherever we have something like autonomous driving in new unseen environments, robotic interactions in unseen environments, or simple, you can also have it if you have an AI system that negotiates with other AI agents. Now, we had this in a way of, because remember here in my first residual AI, we had a base model that was based on the diffusion policy. So we had behavioral cloning in our imitation learning. And then on top, we had a layer with a residual model. And we had corrections for robotics assembly that were trained on reinforcement learning. But we had to have our behavioral cloning from the expert system, and then our corrections is exactly what they were. They were just corrections, and we had a little epsilon we could play around. But now in this case, the epsilon is gone. We have the complete action space, and to be more correct, the complete policy space in reinforcement learning to be explored, and we can learn in this space. So self-play is now a new fundamental technology in advancing AI research, offering here a new pathway to develop intelligent systems that learn and adapt autonomously. And they might even surpass human-level performance in complex tasks, and they generate innovative solutions unconstrained by the human knowledge and the human experience if a human acts here as an expert in imitation learning. So this is really nice if you compare this to our reinforcement learning-based fine-tuning from Princeton, UC Berkeley, where we were looking here only add modifications, but not to explore complete new spaces. And this is a publication from our colleagues in China, a survey on self-play methods in reinforcement learning. I highly recommend this paper, August 2nd, 2024, and they go in detail here and explain why self-play is so important. And think about it. If you have a simple, let's say, LLM, and this LLM is a small one and has only one particular task, and if you take this system and you give it here in a real controlled environment with a version of its former self from the training step before this, and you enable now those two systems to learn. So what you have a very task-oriented environment, a very restricted environment that the system really can search for a better solution to a clearly defined problem. So this means you are not with some general model that knows all the, 5 billion problems of the internet and tries to learn 4.9 billion problems of the internet, but you have one focus, one topic, one small LLM or vision language model, a control environment that is only focused on your one task, and then you let it learn, but only on this path forward. And you are looking here, 10,000, 100,000 run, but find the perfect solution and find a solution that is even better than a human solution. Real nice self-play, something I learned here doing this video, and I would like to share here what I learned. So we move here from a single agent reinforcement learning to a multi-agent reinforcement learning, and we have a lot of problems and we have a lot of new complex dynamical patterns that we have to deal with. And yeah, this is a cooperation also not only from Tsinghua University, but the Tsinghua Berkeley Shenzhen Institute, a cooperation here between the Tsinghua University and the University of California, Berkeley. And I learned here that in 2018, the city of Shenzhen agreed to spend 220 million on this institute. So amazing cooperation. And the authors of this study also propose here a new unified framework. So you not only learn here a little bit of the history in this topic, but they also take a step further in their AI research. And their particular research introduces here a unified framework that categorizes here the self-play algorithms in 4 categories. We will look here at 2. We look at the policy space response oracle series, and in my last video, we look here at regret optimization for imitation learning, and now we look at regret minimization in reinforcement learning for multi-agent system. So what we have here, new, an introduction of an interaction matrix to represent the opponent sampling strategies, and the integration of a regret minimization series into the framework, enhancing here the performance further in our self-play scenarios of multi-interactive agents that we optimize with reinforcement learning. Beautiful. As I told you, this regret gap or this regret minimization, I showed you here to do this here for a multi-AI system with imitation learning, and today we look here at the regret minimization in reinforcement learning. So you see the same idea but applied in different sectors of research. Now for my green grasshoppers, a very short summary. We have our key components of reinforcement learning. If you're new to this, we have a state, represents the current situation or the environment that the agent is in. We have the actions. This is simply what an agent can do. In self-play, actions are the move or the decision that an agent can make actually in the game. Then we have the reward function. So after taking an action, the agent receives a reward or a penalty in the negative case based on the outcome of the action. And this reward helps the agent to learn which action leads to better outcomes. And then we have a policy or a strategy, if you like to call it, that the agent follows to decide its actions based on the state. The policy is refined over time as the agent learns more and more from its experience, from its interaction with the environment. Now you know that reinforcement learning in its mathematical core, we model it as a Markov decision process. This is a mathematical framework that describes an environment in terms of state, action, transition, and rewards. And within this, agent operates by observing states, executing actions according to defined policies, receive the rewards, and transition then to new subsequent states. And the primary goal of this reinforcement learning algorithm is to derive the optimal policy that yields here the maximum expected accumulated reward over time. The transition from a single agent to a multi-agent reinforcement learning, MARL, introduces complex dynamics because we have now the interdependence of the agent's actions. They introduce significant challenges to the stability and the dynamic of the system, as the environment now appears non-stationary to each agent. And again, the main issues here in our multi-agent reinforcement learning are the coordination, the communication, and the equilibrium selection, particular of agents in competitive scenarios. And with the help of game theory, Markov game theory, mathematical framework, that interactions between those multiple decision makers are now calculated, self-play emerges here as a very elegant solution to some of those inherent challenges that we have with multi-agent reinforcement learning. And by addressing those issues, such as non-stationarity and the coordination, this self-play offers now a very focused approach where an agent interacts with copies or past versions of itself. And this past version of itself, like you see here, let's say this is time step, I don't know, could be 60, 70 years old. So this is time step 70, and here you see him time step with 71 years old. If you continuously communicate with your younger self, let's say on a human basis, and you ask yourself, hey, what did I learn? What did I do wrong at that time? How can I improve my actions? How can I improve my decisions? How can I improve my policies that I applied to reach my goal? This is now interesting. And you see, you are just focusing here on your world, on your person, on your targets. And you do not try to be a general AI system that has to solve all the 5 billion problems here on the internet, but you just care about your interaction with the environment and how you can improve. And this is why self-play, I didn't notice it for so many years, but now I find it absolutely fascinating. Talking about so many years, doing here the preparation for this video, I found here the literature to this. Look at this, July 2018. We had also here multiplayer games with deep reinforcement learning, DeepMind, or 2020, June 2020, a comparison of self-play algorithms under a generalized framework. Or if you really want to go back here, and I try to find here the very first ideas, this happened in December of 1962, numerische Mathematik. Or if you then go 2017, a unified game theoretic approach to multi-agent reinforcement learning. And just to be clear here, DeepMind, they did not have access to our beautiful AI models at the time, at 2017, but the mathematical theory of the game theoretic approach for multi-agent, and those agents were not as intelligent as they are today, but the mathematical power apparatus was already there. And if you want to learn here about our point, we're going to focus on the policy space response oracles. This is a publication I would recommend to you. And then, of course, if you're familiar with this, here I think this is one of the latest, the best of the latest publications here. End of May 2024, And we have the policy space response oracles, and here a complete survey, so you get a good overview of all multi-agent learning system in this particular field. Beautiful. So let's start. Let's have a discussion with our younger self, with our older self. Let's see what this methodology is able to do. And as I told you, I would like to focus here on policy space response oracles. This is historically a generalization of the double oracle. And if you don't know about this, a double oracle traditionally focused only on actions within the game theory. And now this extension here in 2017 extended this by considering now policies. And you know, policies are a set of actions and decision across the various states, instead that we focus on single actions. So this year, 2017, was a major step in the development here of our game theory that we use today for our a little bit more intelligent agents, LLMs, VLMs, vision language action models. And this flexibility of this new methodology allows now for any type of a meta solver to be integrated into the framework. And to my green grasshoppers, a meta solver simply computes the meta strategy, which dictates how policies are chosen and adapted based on the learned outcomes and strategy from the previous interactions. How do we learn? If you want to have just a definition of all the elements that we will need, of course, here the core algorithm is here our policy space response oracles. Instead of focusing on individual action like before, like traditional game theory, this new approach now operates here on the space of policies or strategies if you prefer this. Then we have the meta game. This is now a higher level game where the choices are not actions within the original game, but rather the selection of the successful policies to use now in our new advanced game, a meta solver, an algorithm used to find here the optimal strategy, the meta strategy to be correct, within the meta game. Oracles was a term I said, what is an oracle? At first I thought here, Oracle here, the company in the US. No. Oracles were simply historically policies that are approximately one of the best responses to the current meta strategy of the opponents. And those oracles are added to the policy pool that we can choose from, iteratively expanding here the meta game. Empirical game. Meta game is represented as an empirical game, a table storing the expected utilities, the payoffs for different combinations of different policies, and parameterized policies of neural networks that generalize across the state space, enabling learning in complex environment without needing here specific domain knowledge. But in general, let's focus here on this oracle part here. And oracle has different meanings in computer science, but in this specific context, in general, it is a black box that can provide answers to specific questions, often used in theoretical analysis to abstract away the complexity of certain computation that we have in our stack. But now in our example here, an oracle initially referred to a policy. This means a strategy of single agent or multi-agent that was kind of the best response or the near best response to the current meta strategy of the opponents. And those oracle policies were computed using methodologies like reinforcement learning. So the key idea is that the oracle provides a good, but not necessarily already the perfect solution within the context of the current game state and the opponent behavior if we have a competitive game. So again, you talk to a copy of yourself, and in this very clearly defined environment, with this clear focus that you want to optimize your own policies for your person, in your environment, for your goals, for your future actions. This is such a beautiful, very well-defined and narrow system that the optimization mechanisms are real powerful. and they give us real good results, and we do not have to deal with these generalized concepts that learn everything at the same time with limited resources. So this now, very nice. Now, if we go here from game theoretical concept and game theoretical approaches for my green grasshoppers, just to give you an idea what you will find in this research paper as a door opener to make you interested in this topic, we have here our Markov game theoretical approach at first. So we have an agent-environment interaction. Our agent, let's say a robotic system or a game-playing AI, Go or AlphaGo or whatever you have on machines, interacts with an environment. The agent takes action, the environment responds by transitioning to new states and providing rewards to the agent. And the core idea behind our Markovian system is the Markovian property, and it makes the future state of the environment depend only on the current state and the action taken, and not of the entire history of past state and action. So we choose mathematically a very simplified state, a very simplified version. And the agent goal in our Markov decision process is simply to find a policy, a strategy to maximize its cumulative reward over time. Now, the extension here in our multi-agent scenario, we can go from the pure Markov games to partially observable Markov games. So what is the difference? Our Markov games, the Markov decision processes can be extended to handle multiple agents interacting within the same environment, leading to our pure Markov games, or the stochastic games like I showed you in my last videos. But in many real-world scenarios, agent may not have the complete information about the environment state. So those partially observable Markov games address this by allowing agents to have only partial observation of the environment, and then we define here those parameters for our methodology. You have an agent interaction protocol, you have a specific policy, but again, what is the objective? The objective here is identical. So each agent in our multi-agent reinforcement learning system in a Markov game framework that might be restricted here to partially observable elements, each agent aims to maximize its total expected discounted reward over time. This is a beautiful formula, and if you've seen my last videos, you know what all of this beautiful notation means. However, if you're not familiar with the notation, never mind what are the key concepts and the takeaway. Our Markov decision process and our partially observable Markov decision processes in the game provide now a formal mathematical framework for describing sequential decision-making problems, either in our single agent or, a little bit more complicated, in our multi-agent settings. And now in real-world systems, normally our agents have incomplete information about the environment and must make decisions based on their individual observation that might not include the complete available space of observables, of system parameters, but you never know everything in real life. And reinforcement learning algorithms we apply to those agents to learn the optimal policy by interacting with their environment and receiving the rewards. And you know how we continue. Now, if we switch more game theoretical constructs, you have the normal form games and the components here in our normal form games, the players, a strategy space, a strategy profile. You have pure and mixed strategies. Mixed strategies have here a probability distribution over a set of pure strategies, allowing here for randomized action. You say, hey, this sounds interesting. We have our classical utility functions, and then we have different game types. We have a symmetric game if the strategy sets and payoffs are the same regardless of player identity and the strategy order, and. We have a beautiful matrix representation, but of course we have also extensive form games. If you look at the game theoretical approach here, if you want to understand it here from a pure only theoretical approach, players and chance, the history and the terminal history, the player function, the information set, the action space, the utility function, the game tree representation, where the nodes represent the game states, or your complete history if you want, and the edges here of our tree represent the actions taken, and each leaf node is associated with a payoff vector given by the utility function. You have strategy profile in extensive forms. Yes, it's a little bit more complicated, but if you want to dive into game theory, I mean really dive into game theory, have a look at this paper, and little warning, you need minimum 1 day for this paper if you really try to understand here all the context. In the simplest case, we want to operate with a Nash equilibrium. So step 1, definition of strategy and the best responses. Strategy notation, what is the best response? You know this formula. Epsilon best response is a strategy that is within a certain epsilon. This means a very small pre-specified threshold of the payoff of the best response. And then you go on, you have your Nash equilibrium, you have your strategy profile, you have your epsilon Nash equilibrium. And then you have here computational intractability. Computing here the Nash equilibrium in complex games can be computational intractable. And from the alternatives, in I think 2 videos back, we were talking here about correlated equilibrium in multi-agent imitation learning. And now we do this here, correlated equilibrium in multi-agent reinforcement learning, when we apply game theory, the framework of game theory, for our reinforcement learning. So you see, if you want to have a deep dive, there's already an established theory over years and years and years of research. So I enjoyed this. I had a little bit of a deep dive in the last 2-3 days into this topic, and I learned about self-play and how important it is to increase the performance here of our systems. So self-play, a real nice idea. And what I wanted to show you, the authors not just looking back, analyzing here the complete history of self-play, but they also had some ideas how to further advance this unified framework of self-play. So what they did, and please read the paper to understand this in detail. I can give you here only an overview. Defining on the inputs, you have a policy population, a policy representation, an initialization here of the policies. You have, again, as I showed you at the beginning, an interaction matrix, and you have a meta strategy solver, so what we know. But now let me focus here on the interaction matrix, because this seems to be a real important component here of this new framework. So for my green grasshoppers in the classical reinforcement learning with self-play, the interaction matrix plays a critical role in defining how different policies interact and evolve over time. Remember, we're here in a multiplayer or in a multiplayer game theory or multi-agent system for our AI interactions to solve complex tasks. And this interaction matrix captures here the opponent sampling strategy, which determines how often and in which manner each policy tested against each other. And this is crucial in multi-agent system where the learning dynamics can be complex and non-stationary. Now, what is the purpose in all of this? And we just look here at the framework here of self-play in our game theoretical approach. We have here the opponent sampling strategy. So this means the interaction matrix represents here the probability distribution over the opponent policies for each policy in the population. And again, we have here a sampling strategy. This is important, fundamental in self-play algorithms, as it influences how policies are selected for training against one another. For example, if you have in the simplest case a 2-player game, this indicates the probability that a policy is optimized against another policy. And this helps us to manage here the competitive dynamics within the policy population by ensuring diverse interaction and preventing overfitting to a specific set of opponents. B, and the structure now of our beautiful interaction matrix, being now a lower triangular or not, reflects here the training paradigm of the self-play method. C, and this is now again regret optimization. This is very similar, if you think about it, to our regret gap minimization in multi-agent imitation learning. And now we have this here in reinforcement learning. So in regret minimization based algorithm, this interaction matrix helps track the historical performance of the policies, which is essential to know for updating the regrets and the strategies. So really important in repeated games like chess or Go or whatever you have, where the goal is to minimize the cumulative regret over multiple rounds rather than focusing here on single episodes. So if you are again into game theory, regret minimization is a topic I would definitely look into. Now, this new framework of self-play, they call it here Algorithm 1. It looks easy, but little warning, it is not at all as simple as you might think, that it's just 9 lines of pseudocodes. Yeah, the execution of the algorithm proceeds through a set of number of epochs. You know this, looping through all our epochs. We have to initialize the policy. So at the start of each epoch, each policy pi is initialized based on the chosen method. Then we have to compute our oracle. The oracle function is called to optimize or adjust each policy based on its current strategy and the strategy of our other players. We evaluate the policy using here our evaluation function. The performance of each policy is assessed and recorded in the performance matrix. And you'll see this can also have a complexity of its own. Oracle function explained a little bit more in detail, but I think this is too much for today. I just want to give you here an introduction here, especially with a strong focus today on this beautiful self-play. Now, if you dig deeper, you will see here algorithms in pseudocode, how to compute the oracle in reinforcement learning and evolution theory. And then, as I told you, in regret matching, if you really want to have this professional deep dive, how to compute the oracle and regret matching, please read the paper. It's an excellent paper and gives you really a good overview. This is regret matching. Remember, again, quite an analogy that we had here with our regret gap, that we had here with the correlated equilibrium in our multi-agent imitation learning. You know the regret in general of our mediator policy, how we calculated here the regret gap, how we had our equilibrium functionality and our optimization. So try to understand how this is working in imitation learning and in reinforcement learning, and then you can apply game theory to the highest extent. And this is it, a very short introduction, just to give you a hint, a feeling, what we are doing currently in AI whenever we apply game theory to reinforcement learning, and we have a system of multi-AI agents acting together, interacting together, acting against each other. How this will play out if we now advanced our Markov decision process to our Markov game, and then to our not observing all elements of the system Markov game, and how we can use and utilize here this beautiful power of self-play of agents if you compare yourself to an older version of yourself, or you talk to a younger version and you try to learn in this interaction what went wrong. Imagine you can go back and argue with yourself after you finished university and you were looking for your first job, where should you go? What should you do? What should you try to achieve as your first career highlight? So this, if now AI system are doing this, and if we enable this AI system to do this for each agent and in a multi-agent environment, this is really a step forward to have a better performance for our game theory applied to reinforcement learning. I hope you found this video interesting. I hope there were some new ideas, maybe some brand new ideas, and it would be great to see you in my next video.